Okay, so I already introduced myself. Today's lecture is going to be a motivating lectures. You all already seem so motivated to do computational fluid dynamics, but I thought I'll give you my perspective for doing my motivation to CFD. But first, I like to give a few slides that I always give to when we do recruiting for graduate and undergraduate students. And historically and traditionally, we all deal with the scientific methods. We're engineers, we're engineering science, we're scientists, depending on what research you're going to be doing. But we all rely on the scientific method. And what is the scientific method? What does it tell us? Come on. So you want to understand a phenomenon. Let's say, I'm dropping this eraser, okay? Something happened here, okay? So there's an observation. You saw that this thing dropped to the ground, right? Okay, then you have to come up with a hypothesis for what is happening there, and then you test your hypothesis. That's the foundation of the scientific method. So the basis is first you start with an observation. So you notice that things fall to the ground. And I picked this example given Newton's notoriety in the example with the apple falling on his head. That's not accurately true, but it's not that the apple just gave him the idea of gravity. It was a result of years of thinking about the problem, and then he saw things falling, and then it kind of hit him. But the observation is that, for example, things fall to the ground, or when you compress your system, you start getting evaporation in certain parts of your turbine. So that's an observation, and you need to explain it. And then the way you explain it, you observe a lot, collect some data, and then you develop a hypothesis or model. In the case of things falling to the ground, Newton said, I'm going to posit a fictitious force, an imaginary force called the gravitational force, and that force is proportional to the acceleration of the object as it is moving down to the ground. And how did he do that? Well, based on observations, he collected some data, he did some measurements, and he came up with a model that describes the motion of things that fall to the ground. It's still a model. The model doesn't care if gravity exists or not. As long as it describes the motion of things falling to the ground, that's as good as it gets, okay? And then the next step is you take your model and test it beyond your observations. So you try it on new things. So if your hypothesis and model says that things fall to the ground at the same rate, so whether you drop a 50-ton ball and a tennis ball, they're going to arrive at the same time to the ground, absence of drag, okay? So you go and experiment with that. And this is actually what Galileo did before Newton's model of gravity. So Galileo went on the Leaning Tower of Pisa, and he dropped things to the ground and measured the rate at which they accelerate to the ground, and was able to come up with some laws for motion that Newton eventually used to formulate his second law. Now, after you do your experiment, you may observe that your model doesn't fit all the experimental results. So what do? You take your experimental results and then you refine your hypothesis over and over again. And by the way, it's called the Leaning Tower of Pisa, not Pisa or pizza, okay? Some people say it's the Leaning Tower of Pizza. It's not. It's the Leaning Tower of Pisa, not pizza. Okay. Okay, so that's fine now. But how do you experiment? And traditionally, this has been the hallmark of experimentalists. And if you've done some experimental work, you kind of say you have kind of pride in your experiments because you're saying this is the real thing. But how do you experiment on an exploding star? I honestly don't. If you're experimenting on an exploding star, I want to leave the country, right? Because that's impossible, and it's probably very dangerous. Like they talk about these experiments about creating a black hole in these accelerators. Yeah, don't want to do that. How do you experiment on a hurricane? How do you do a hurricane in a lab? I mean, we can create some cyclones with water, right, or with some air, but then, how do you recreate the destructive force of a hurricane? You can't do that. And if you can, it's probably very expensive. So all you can is either observe the real thing or simulate it. How do you experiment on a nuclear accident? How do you run fail scenarios? You can't just, turn the cooling water off and let your nuclear reactor blow up. We've had a few of those happen in real life, Chernobyl, Fukushima, and those were really terrible. So we can't really experiment on things like that. How do you experiment on a coal boiler? I mean, a coal boiler is something tangible. We can see, we can look at it, we can put probes. But the probes are only going to give us so much information before they melt, and they may only give us kind of integral quantities, integral values about the system, like the total heat transfer rate, or how much CO2 you're emitting from the coal boiler. But they're not going to give you kind of detailed description of what is going on at every point inside the coal boiler. How do you experiment on flameless combustion? If you can't see a flame, there may be a flame taking place instantly, volumetrically in this room. It will burn you instantly. So we can't really experiment on flameless combustion. You have to put that on a computer. How do you experiment on something that takes decades to form? Precipitation. If you've ever entered a cave, or if you look at your shower head, if you live in an area where there's minerals in your water, specifically calcium, you're going to see some calcium deposits, but it takes probably a month for these calcium deposits to form. And in real life, precipitation takes place in caves. It can take 1,000 years. And how do you do that? Precipitation or carbonation, for example, is one example of how nature can store CO2 in carbonates. But it can take decades to form precipitates. And so how can you experiment on something that takes a decade? You can't run an experiment and write a note for your future grad students. Keep the experiment going. I'm going to die, and you all are going to die. But in 1,000 years, we're going to publish our results in Nature. You can't do that. Okay? The reality is that many experiments and many systems are so complex that it's expensive, dangerous, or practically impossible to actually do experiments, to use the traditional scientific method where you observe, develop a model, and experiment. And this is where simulation comes in. You're no stranger to simulation. You've heard of simulation science, scientific computing, all kind of the same word. It's a new kind of science, and it's historically been frowned upon because it looks like just cartoons. You're putting cartoons on a screen, right? How can you trust a simulation? Your simulation is only going to be as good as the models it is trying to put on a computer. But I'll tell you, we will learn how simulation can overcome experiment eventually. But now the new way of doing science, and thankfully simulation has become more and more accepted in the scientific disciplines, is that we're going to take these experiments, we're going to develop basic laws, so essentially Newton's laws of motion, or how particles aggregate with each other. You can do an experiment on that, and then we take those little models piece by piece. We're going to put them together and create a simulation of all the nonlinear and complex interactions between these basic laws, and run a simulation and then refine our hypothesis and model. So then the role of experiment becomes to develop the fundamental laws of how things behave and operate in an isolated fashion. It's like when you go to the gym and if you've done weightlifting in the past, you can use machines and you can use free weights. What's the advantage? What's the pro and con of each? With machines, you can focus on one set of muscles. If you're doing presses, you can focus on your chest and maybe a little bit on your upper arms. Or if you're doing curls, on the machine, you just focus on your biceps. But if you're doing dumbbell curls, you're like standing, you're trying to stabilize yourself, you're using your core muscles, all of these things together. So experiment serves the role of a machine now, of a gym machine. It gives you targeted investigation of certain basic laws. But simulation brings all of these laws together, all of the little muscles that you're using, and puts them all together to create one full investigation of a complex system. Okay? So simulation and computation. So you can use my notes. I'm going to post all of my notes on my website. We'll discuss this at the end of the class. But you can use these as your lecture notes. You can take notes, and I'm going to give a lot of handouts from textbooks. So you don't need to buy any textbook. I'll just scan the chapters that are relevant, or just kind of download them and share them with you. So you don't have to worry about that. But I want you to focus with me here, because you'll have access to this, and I'll try to post these slides before the class, so if you want, you can print them and take notes on them if you like. But simulation and computational methods, or in general scientific computing, now have been hailed as the third pillar of the scientific method. So what are the other two pillars? There's experiment and theory, right? So theoretically, you can think about something, just like what Einstein did. He theoretically thought about relativity and came up with experiments theoretically just by thinking about it. And so there's theory, there's experiment, and now there's simulation as the third pillar of scientific computing. But we're not learning about scientific computing here. Scientific computing is a big field. There's DNA simulation, there's material simulation, there's chemistry simulation, there's molecular simulations. In this class, we are going to be focused on fluid dynamics simulations. And indeed, if you look at any simulation, the most attention-grabbing simulations are those that involve fluids or things that are moving, because fluids are fun and interesting. You know, you're driving downtown, you're not going to look at the Goldman Sachs building that's, you know, standing like this in the wind. It's probably shaking a little bit, but it's not interesting. You're going to look at the smokestack from all the industrial flares that are operating in the city. You're going to see all the structures coming out. You're going to look at the clouds, how they kind of have these instabilities in them. And you're going to look at the weather systems because there's fluid dynamics. It touches all of us. And so these are some examples of work we did in my group and my extended group. Just to show you kind of how cool how it can grab your attention, how a CFD simulation can grab your attention. This is a computational fluid dynamics simulation of a coal boiler. This is a pilot scale coal boiler. It's probably actually just this big, okay? And we are injecting coal tangentially at all of these points over here, and these are kind of the boundaries of the injectors. So you are injecting coal particles. They're represented as particles or as a gas. That's a different story. But you know, we are injecting them, and they are swirling, and things are going on, and then they exit from over here. Now, what I'm going to show is, so this is interesting and fun, but okay, so what? What do you do with this data, right? So, pardon me?
That's really fast. It all takes place in less than.
Well, we are accelerating, yeah. But it's a small scale boiler, right? So if you do scale similarity, you'll see kind of how this operates at a larger scale. But I'm going to take a slice over here, okay? And if you go to a real boiler and put a camera in there and take a snapshot of what is going on this plane, this is what you see in real life. That's called the fireball, okay? And it kind of looks mushy because it's really fast, and your shutter speed is not going to capture, you know, the fastest shutter speed is probably 1/60 seconds. So it's going to smooth things out a little bit. So it kind of gives you an average description of what's called the fireball in an industrial boiler. Now I'm going to take the results from my simulation and put them on top. Okay. This is starting up. The coal is coming in and starting to fill it out, and then it's starting to mix and rotate. And you can see that qualitatively, we're actually capturing the trend. But not only on average, we are capturing the trend instantaneously. As we are injecting so let me run it again. As we are injecting the coal and, you know, transported by the gases into the coal boiler, okay? So this is what simulation, this is what CFD can give you. It can give you instantaneous information about what is going on in a complex system like a coal boiler, but also point-wise. So now at every point, I can pick this point and say, okay, plot the velocity over time. What is the velocity? What is the speed over here? Or what is the concentration of coal particles? Now remember, this plane, there's coal coming from the bottom as well, because, you know, part of it goes down and then comes back up, and there's coal exiting. So, you know, there's change going on in 3 dimensions as well. But this is what CFD gives you, okay? This is another simulation from our group by Professor Smith. This is called a pool fire. So it's essentially if you, by mistake, drop like some jet fuel on the ground and it lights up, what happens? How does it light up? Now, this was part of a Department of Defense project. They were looking at, you know, if they were transporting weapons and somehow the truck that's transporting the weapons gets into an accident and there's a gas spill and the gas lights up. Would this fire actually light up the payload? Okay, so the next simulation would be a cylinder placed in between and looking at the heat transfer from this fire into the weapon. But this is just to show you that, these are attention-grabbing simulations, okay? And they're all done based on fluid dynamics, okay? This is another simulation from our group. This is a flare. So typically flares are used in industry to, to release all the gases in an industrial compound overnight. So you don't want to shut off your machinery because it's costly to really get them started the next day. So you just let them run through the night. You just burn all the gases and then come back the next day and run it again. But in this case, Jeremy was investigating the cross flow over a flare. They were doing some experiments to measure, they were trying to measure some of the emissions created by the flare. But anyway, they wanted to look at the flow around the flare. So this is the flare column, and there's flow coming in, there's air coming in, there's wind coming in from West Valley, for example. And how is this wind going to impact the fluid flow behind the flare? What you're looking at are vorticity contours. Do you remember what vorticity is? It's from your fluid dynamic. What's vorticity? Okay, who has taken undergrad? Okay. Yes, so it has to do, it measures the rotation of a fluid. Okay, how much rotation there is in a fluid. So if you have flow that has equal velocity across and that is moving forward, there's no rotation because all the fluid particles are moving at the same speed. They're parallel to each other. There's no rotation, there's no spin, like you said. But when different fluid particles are moving at different speeds, they're going to interact with each other and they're going to spin. They're going to start rotating, and they create this thing called vorticity. Vorticity is very important in mixing. So when you put sugar in your coffee cup or in your teacup, what do? You get a spoon and you spin it, you mix it. You're creating vorticity. You're just shaking it, right? If you've seen a barista, what they do, they start kind of tapping with or if you've ever done Turkish coffee, you get the spoon and you kind of tap it at the bottom to kind of shake things off. So you're creating mixing in the fluid. And so this is a measure of mixing. It tells us, it informs us kind of how this boundary is affecting these vertical structures that are flowing around. Anyway, okay. So like we said, the most notable and attention-grabbing simulations are those that involve fluids. And that was the purpose of the last few simulations, is to just kind of grab your attention. But this is no surprise, because we live in a fluid. I mean, it's funny, sometimes we think of sea creatures as living, immersed in water. We are immersed in a fluid as well. We are immersed in air. We live in air. Without the fluid we are living in, we cannot survive. So we're like sea creatures, we're air creatures. We can't fly, unfortunately, but sea creatures are truly three-dimensional. They can move in all directions. We can only move on the surface of the earth, right? But fluids are all around us, from the air we breathe, from all the devices that we use. There's fluid dynamics involved. Water, when you're washing your hands, when you're drinking, when you're eating, when you're driving your car, there's fluids involved, okay, everywhere. And so that's why we are drawn to fluid dynamics, because fluids are part of us, okay? We are made of fluids, right? And, in terms of engineering applications, there's internal combustion engines, airplanes, vacuum cleaners, dentistry tools. Like, seriously, when you go to the dentist, I'm going for dental cleaning tomorrow, and they use this insane, they scrape your teeth. But there's also one other tool that I asked for. It's called an ultrasonic device. It's much easier on the teeth, but it's a jet of water at very high speed and just kind of cleans all the plaque and buildup on your teeth, and so dentistry tools. And also when they're drilling, they're also kind of, there's water coming out. Pressure cleaners, I don't know, for lack of imagination, I just put a bunch of things. But there's fluids everywhere. Okay, so why then do we need CFD? It's because the behavior of fluids is really complex. I mean, scientists have dedicated their lifetimes to study fluids, and still it is hard to do predictions of complex fluid flow, especially turbulent flow. So we need CFD because we need a way to study and predict fluid behavior. Okay, so since fluids are at the heart of a large number of complex systems, it does make sense to study fluid dynamics. And traditionally, the study of fluid dynamics involved theoretical, experimental, and computational techniques. Okay. Now we're going to go over. So now what we've set the stage for. We're setting the stage for CFD. We said that the most attention-grabbing simulations are those that involve fluid dynamics. Okay, and I hope you agree with that. Okay. I saw this morning an electromagnetic simulation that was posted in the MEB building. So if you're walking by, going to the ICC lab in MEB, that's kind of on the second floor, right before my office, there's like this picture. Actually, a colleague of mine did this in electrical engineering. They have the University of Utah U symbol and with arrows in it. I'm like, okay, so what? There's just magnetism and it's just arrows. And then you change the magnetic field and the arrows move a little bit and that's it. And to me that's like, okay, it's a basic diffusion problem, That's not very interesting compared to when I look at the coal boiler or the pool fire and seeing this happen on a computer. So yes, the most attention-grabbing simulations are those that involve fluids. But we also understand that fluids are very important to study, okay? But they're complex and they're hard to study. And historically, there have been two ways, and recently there has been the third way. The first one is theoretical. Or analytical methods. So if you've taken fluids, you remember Poiseuille flow, for example. That's the classic parabolic profile for the flow in a pipe. And actually, Poiseuille was a medical professional. He wanted to study the blood flow profile in arteries. And so he approximated the artery as a cylinder and with a fixed pressure gradient. So there's high pressure at one end, low pressure at another end, trying to mimic kind of the action of the heart. There's high pressure here and low pressure there and how the blood flows. And he derived an analytical solution for the flow inside a pipe. Does it model the flow inside complex arteries? Absolutely not. But in a small section of an artery or in a small section of a pipe, you can pretty much approximate the flow using his analytical solution. So analytical solutions are very helpful. I've done a lot of work in analytical work for fluid dynamics. They're very helpful to give you basic insight into what's going on in a flow. We call these very low order models. So in the absence of all complicating features, what does the flow look like? And you can get an analytical solution, but that's it. And it's usually limited to very simple geometries, flow in a cylindrical pipe or flow in a channel, flow in a 90-degree bend, but that's it. There's no way you can analytically get solutions for the flow in like a coal boiler or flow over a flare, okay? Next come experimental methods. They're the most realistic, but they can be expensive. Trying to run wind tunnel experiments, you gotta buy equipment, you gotta set up your experiment correctly, you gotta figure out your scaling laws, you're gonna run your experiments over and over and over again, and they cost a lot of money. Okay, if you've done, I've done very limited experimental work, and budgets for experiments are over 10 times higher than budgets for computing. And so, they're very expensive. And especially for companies like Boeing, when they're trying to develop a modification to one of their wings, for example. If they want to run experiments on 1,000 wings, that can bankrupt the company because, the cost. How many airplanes does Boeing make? 100,000? Well, you're probably going to have to experiment over 20,000 wings or 10,000 wings or 1,000 wings, and that's very costly. Just building a wing every time over and over again, whether you build it at a small scale or larger scale, that's still costly because you have to wait for the wing to be manufactured, you have to ship it in, and then run the experiments, and then, oh, it's a failure, so you have to run it again, okay? But they're the real thing. If you are looking for what goes on in real life, you better start with, you better do an experiment. And finally comes in computational methods, where, like we've seen before, we can take theoretical models and combined with experimentally derived laws and put them together in what we call the governing equations and try to solve these equations instead. So what would happen if we try to mimic reality? So reality, in a way, is solving the governing equations of fluid dynamics instantaneously. They're just different particles responding instantaneously to each other as the flow takes place. Computationally, we're trying to mimic that, okay? But they can provide unbelievable insight. Okay, so here's a little table that I took from Professor Rob Stoll in mechanical, discussing the pros and cons of analytical, experimental, and computational methods. So here on the left, on the first column, you see the approach, analytical, experimental, computational, and the next two columns discuss the pros and cons. So for analytical methods, they're clean and exact, simple. You can get a closed form solution, parabolic profile for flow in a pipe. They are in formula form. They're simple. You can just apply them at any point in space and get the velocity field, for example. But they're restricted to simple geometries and physics. So sometimes you have to assume the flow is inviscid, okay? Or you have to assume the flow is Stokes flow. That's purely viscous. There's no convective action going on. Experimental methods, they're the real thing, okay? If you want to look at the real thing, you better do an experiment. But they can be costly. It can be hard to measure quantities of interest. Like you cannot directly measure vorticity, I would imagine, and you kind of have to derive it from measurements of the velocity, okay? And there are certain things that are difficult to measure. You have to derive it from other measured quantities, okay? You get into measurement errors and just setting up your experiment. Like again, let's say you wanna do the hurricane. How do you scale the hurricane to run it in the lab? Okay, so do you use another fluid? Do you have to use water? But then when you use water, you have to change the properties of every other thing, and some other things do not scale probably. There's no scaling similarities for building materials, for example. Computationally, you can solve complex problems. Just throw it in on a computer. You can add as complex physics as the simulation allows you, as long as you can converge to a solution. And it's typically less costly, okay, than experimental methods. It's probably 10% of the cost of running an experiment. So with 10 experiments, you can run, with one simulation, you can run 10 experiments, essentially. So that's a lot, okay? And depending on kind of how much computational power you need. But, numerical methods or computing, CFD, suffers from other things. There's modeling errors, there's truncation errors, there's stability issues. You may not be converging to the correct solution. We'll touch on all of these. You may be simulating the wrong thing, and we'll see. All of those come from the fact that we are going to approximate the true governing equations using discrete numbers. Okay, so now we are ready to define CFD and limit the scope of what we are going to discuss in this class. And I've taken this definition from Gretár Tryggvason. He was the editor-in-chief of the Journal of Computational Physics. Brilliant guy. He does direct numerical simulation of multi-phase flows. But you can think of CFD as computing, and we're going to limit. This is going to limit the scope of this course. We're going to focus on computing multidimensional flows. We may be stuck with 2D for all practical purposes in this class because 3D is going to be expensive for us. But computing multidimensional flows governed by the Navier-Stokes or Euler equations. Okay, and those two equations you've probably heard of. We'll discuss what they are. The Navier-Stokes equations govern the flow of incompressible fluids, incompressible flow. The Euler equations, they're the inviscid version of the gas dynamics equation. So if you're looking for compressibility, shock waves, we look at the Euler equations, or their viscous version, with the goal of obtaining physical insight and quantitative predictions into complex flow. That's what CFD is. So we're not just randomly solving PDEs, partial differential equations, although the Navier-Stokes and Euler equations are partial differential equations. But they're very unique. And over the course of the semester, we're going to understand their uniqueness. But they're not just your arbitrary partial differential equations. There is certain uniqueness, specifically with the coupling between the velocity and the pressure, and how the pressure can be used to enforce mass conservation. That is unique to the Navier-Stokes equations. That is not found in arbitrary partial differential equations. However, the methods used for partial differential equations are used in CFD. So we're gonna limit ourselves to, we're gonna look at PDEs initially, like the advection equation, the diffusion equation, advection diffusion. We're gonna see kind of how to solve these problems, because they at their foundation, the Navier-Stokes are advection diffusion equations. But then we're gonna have to add this unique thing that is just unique to fluid flows, okay? So therefore, CFD is only a subset of scientific computing. Scientific computing is a big field, but the most interesting are CFD simulations, in my opinion, okay? And you can combine fluids with solid mechanics. So if you're doing fluid structure interaction, for example, you want solid mechanics, but still our focus is going to be on fluids. So then CFD is indeed a multidisciplinary topic. So it's kind of confusing being a CFD person in chemical engineering, but I have to know a lot about programming, computer science, and applied math at the same time, more so than chemical engineering processes. In fact, you reach a point where you forget your chemical engineering. You just focus on the mathematics and the computing that's involved. But we're going to try to maintain, equal footing in all of these. So numerical methods, that's the applied math, fluid dynamics, and any other phenomena. So if you have reactions going on, if you have structural dynamics going on, you have to understand the remaining parts. But fluid dynamics is the guts. And computer science, so that's where the programming aspect comes in. Okay, so now that being said, now we've defined CFD to the computation of fluid dynamics, not just numerical methods. We can look at a historical perspective. I always like to give, to look at the history of something. And if you end up doing a PhD, or most of you are in grad school, you should get a bird's eye view of who did what since day zero, okay? Who was the first to start this? So the history of CFD can really trace back to the early 1900s. In fact, you can go all the way back to Euler with the Euler method. But there's this guy called Louis Fry Richardson. He wrote this book. He was very ambitious. He wrote this book called Weather Prediction in Numerical Process in like 1910. And look at how brilliant that guy was. He took the Earth and split it into zones. These are going to be our finite volumes we're going to learn, or grid points that we're going to learn how to use. And he computed the velocity and the properties inside each one of those zones. Each zone was like 10 or 100 kilometers wide. But look at how brilliant he was. His method was unstable, and he didn't know that, thankfully. Otherwise, he wouldn't have published the book. But he published it, and I'm going to put the paper on my website for you if you're interested to look at it. It's just fascinating that someone, we think of people in the past as the being less knowledgeable than we are. In fact, I believe they had more insight and more wisdom, because we personally now today rely so much on Google and other things and others. We use the reference book mentality. We always want to seek a reference of like, yeah, how do I solve this, or how do I do that, rather than trying to figure it out ourselves. So the first couple of hints towards fluid dynamics were Richardson and Whittaker and Robinson, the calculus of observations. Courant, Friedrichs, and Louis, they implemented, they came up with a criterion for stability of numerical methods. So that's still not CFD. This is just numerical methods. This was kind of the closest to CFD, but these guys are mostly kind of just numerical mathematical analysis. But they were really setting the foundation for what is to come when we're doing CFD. And many papers also followed in the 50s. They were mostly focused on partial differential equations. So iterative methods for the solution of finite difference approximations of the elliptic equation, that is going to resonate with the pressure equation. How do we solve the pressure equation? The pressure equation was an elliptic equation. So there you go. We have a recipe to solve an elliptic equation. Stability analysis for Courant, Friedrichs, and Levy. Point vortex simulations. So those were the closest to a fluid simulation in the 30s. where they simulate fluid particles as point vortices that have certain strength, but it's not a good computational fluid dynamics method. But it was an early attempt. Von Neumann stability analysis of finite difference schemes. So these are still not full CFD. Then conservation laws for governing equations by Lax in 1954. You're going to hear things like Lax, Wendroff, Harlow, and Wells. These are the big names. These are the guys who started CFD. And a bunch of other things, Lax, Wendroff method. Those are still just numerical methods. But CFD in the modern sense started really, given our definition, and the bias we have for the labs, is started at Los Alamos when the formation of the T3 group in the 50s. First, they were interested in doing compressible flows, and this was really kind of in weapons development. So it's funny how military investments always lead to some of the biggest breakthroughs in science and societal change. Then these guys came up, this group came up with methods for incompressible flows. So the vorticity stream function approach, that was one of the first methods to take the Navier-Stokes equations and get rid of the issue that there's no equation for the pressure. And I'll discuss that in a few slides next. Then they came up with the marker and cell method, and this method actually survived to this day, and that gave birth to what's called the staggered grid. Some of you know what the staggered grid is. It traces back to Harlow and Welch in the 60s. And then all speed flows with the ICE method. We had a faculty member in mechanical. Todd Harmon actually does ICE. We have a code called ICE. Pat McMurtry was a faculty member in mechanical engineering. He's retired now. He did ICE. And some other methods. Now, this was the first paper by Fromm and Harlow. You will hear Francis Harlow. He passed away in 2017. Big name in the development of computational fluid dynamics. One of the first papers in physics of fluids. He was looking at the flow behind a cylinder. There's a cylinder right there. And for a certain Reynolds number, okay, who doesn't know what the Reynolds number is? Okay, who knows what the Reynolds number is? Come on. Okay, so for it measure, the Reynolds number is a measure of how much inertia you have, how much movement in the fluid you have, versus how much drag and friction against your motion there is. Okay, so high Reynolds number flows, you have a lot of motion and less viscosity, less drag. Okay. So for a certain Reynolds number, for a certain value of the Reynolds number, based on the cylinder diameter, you can get the formation of vortices called the von Karman vortex street. If you want to Google that, von Karman vortex street, go and Google it and see some of the most beautiful images from satellites about vortices being created behind a cylinder at a very specific range of a Reynolds number, like between 100 and 250. Okay, it's purely laminar flow, but you see the formation of these vortical structures. And they did this with the vorticity stream function method. And then they developed also Harlow and Welch. They developed the MAC method, marker and cell method, where they put markers in cells and they simulated what's called the dam breakup problem. So what this problem is, there's a channel, you have some fluid here protected by a screen, and then you suddenly remove the screen. What is going to happen? The fluid is just going to collapse, and then it's just going to go all the way and hit and splash and come back. But what survived from the marker and cell method is this grid, what we call the staggered grid. And we're going to learn why this grid is so important for computational fluid dynamics. It essentially tells you that you can place different quantities at different locations, or you have to place different quantities at different locations on a grid for you to be able to get a consistent solution. Okay? Now, in the 70s, there was some exposure, or late 60s, there was some exposure to CFD, but it was still not that popular. So again, Harlow and Fromm, and also Harlow and Shannon, they published in Scientific American and in Science what they've been doing. And that was amazing. Like right now, you don't see papers about CFD in Nature or Science Magazine or National Geographic. No one is publishing even papers about simulations there. But these guys in the 60s and 70s, they were able to get these papers out. But still, people were not interested. It wasn't time for it yet. There was significant distrust and disdain, actually, towards simulation. And I'm going to show you a piece of an article that I will assign you to read by Francis Harlow. It was his memoir before he died, and it's on my website. I would like you to read that article. So this is a snapshot from that paper. Many of these results were published in reports and journal articles, but not without opposition. There was, for example, a conversation that was reported to me, Harlow, which took place around 1955 between two of the upper-level managers of the theoretical division. So, in the labs, there's like a manager for a group, and then, upper-level management, and they govern groups. Elizabeth, you know about this because you work in the labs. So anyway, two upper-level managers, one of whom said, look, what is this stuff? They were talking about the PIC method. That's the precursor of the marker and cell method. You don't have to worry about these, but it's one of the methods it's the particle and cell method. So that was one of the methods they were trying to develop to simulate fluid flow. This PIC method that they're trying to publish a paper on will never work. Look at the narrow-mindedness in this upper-level management. There will never be computers big enough and fast enough to solve problems with all of the particles that you need in order to resolve what's going on. I don't think we should publish this. And the other person said, hey, look, maybe it's not useful or won't work, but on the other hand, it's something that was tried. So let's just kind of publish it, and then, who cares? But then, thankfully, Harlow says, I'm happy that the second point of view prevailed. Another type of opposition occurred in our interactions with editors of professional journals and with scientists and engineers at various universities and industrial laboratories. One of the things we discovered in the 60s and 50s was that there was a lot of suspicion about numerical techniques. And I still want you to be suspicious. Someone comes and shows you a simulation, you're like, this doesn't make sense. So if you watch a movie, like one of those Disney animation movies, you see a lot of fluids going on. Those are not real. They're statistically correct because they show you the trend, that a wave splashes on the beach and it just does something like this. But that's not quantitatively correct because you cannot get the velocities correct, you cannot get the pressure correct, but they are reduced methods to show you visually what your eye has been trained to think is right. But they're not correct by all means. So a numerical simulation, you should be suspicious of all numerical simulations. But these are editors of journals. They were suspicious of, what was that? Computers, a large suspicion about numerical techniques. Computers and the solutions you could calculate were said to be the playthings of rich laboratories. So they thought they were spoiled people in the labs who are doing this, and this will never take off. You couldn't learn very much unless you did studies analytically. The truth, of course, has turned out to lie in the complementary interaction between calculations and analysis, and in the validation of both computations with experiments. Anyway, so this is from Harlow. His paper is on my website, tonysaad.net, and I'll discuss this in a second. In the 70s, CFD goes mainstream, but it was mostly thanks to commercial codes, but it was still unimpressive to the general public. And this is when commercial codes took off, and Brian Spalding, one of the big names in CFD, you'll probably hear his name as you look at turbulence models at the end of this class. He was one of the advocates of doing software that is commercial. But for commercial software, what do you want? For commercial software, you want things that just work. You will learn in this class that 1 out of 2 times your numerical method is going to fail. And you're going to be like, oh, what is going on? And then you're going to have to analyze it and figure out that, my time integrator was unstable combined with this spatial discretization, or my spatial discretization was dispersive, and things like that. And you have to go into the guts of it. Commercial codes can't do that. You can't just run a complex boiler flow, go for the night, sleep, come back the next day, and the simulation has crashed. You can't afford to do this. So commercial codes sacrifice accuracy and correctness in numerical implementations for the sake of robustness. And that's okay. And that's okay, because then the role of a commercial code is to give you an idea of where you need to start your experiments at. So if you can save your 50, 60% of experiments, that's great. You've saved the company a lot of money. And you can do this with commercial codes, okay? ANSYS, Fluent, Star CCM, OpenFOAM, COMSOL, they're all commercial codes. If we have time, we'll try to cover a lecture. It's been a long time. I haven't touched any commercial code, but maybe we'll figure something out this semester to look at a commercial code together, or one of the projects you're welcome to do in a commercial code. But today things are different. Today people, if you're not doing big data or simulation, you're like your paper is not worth it, okay? And what changed? It's really computational power that changed. So there's this website called Top 500. It lists every month, it lists the top 500 supercomputers in the world. And this is one of the most recent ones in June 2018. Summit is currently ranked in the US, currently ranked as the top supercomputer with peak performance in teraflops. So what's a flop? Yeah, it's a floating point operation on a computer. So that's essentially when you multiply two numbers, when you divide two numbers, when you add two numbers, when you subtract two numbers, that's a floating point operation. And when we say that Summit can do 122,300 floating point operation, 122,300 floating point operations per second, it can add and subtract and multiply. That's a lot. Okay, that's a lot. And so, but these performances these are the peak performances. Your code is not necessarily going to be able to achieve that peak power, but there's potential to achieve that peak power. So this enabled the calculation of more and more accurate fluid flows, and that led to more belief in these simulations. Okay, all right. So what are the ingredients of CFD? There's lettuce and broccoli and cucumbers. Overall, you want to do three things before you embark on a CFD journey. Okay, even if you're using commercial software. First, you need to identify your physical process, and we'll discuss this in a second. Develop a mathematical model and a numerical model. Okay, so we start with the physical process. You look at your problem, and you ask yourself, is this flow compressible or incompressible? So is there a lot of density changes in your flow? Is the pressure so significant? Are changes in pressure causing significant changes in density? For example, this is a compressible flow because there's this sudden change in pressure and sent a shock wave in this chamber, and you instantaneously heard it in your ear. This is a compressible flow. But if I do this, that's not a compressible flow, okay? That's a very low speed, incompressible flow, okay? Now, is this flow laminar? Probably, yeah, it is laminar. But if you guys were dancing around in the room and jumping around and someone, turns on the fan, that flow is going to be turbulent. So you have to identify where you're at. And this comes from your engineering insight, okay? If you're looking at emissions from a smokestack, you're most likely turbulent, but you can be incompressible or incompressible with variable density if you have some reactions going on. Okay, you're open in the atmosphere. In airplane flying, that's still kind of incompressible flow, unless you're looking at military airplanes. Then you want to look at compressible flows with shocks. Okay. So identifying the physical process, is there combustion, reactions, moving geometry, all of these things. You have to set the stage for what you need to solve. In the end, you're asking the question, what am I solving on the computer? Okay. Next, in light of your physical processes, you want to develop a mathematical model for these processes and a solution algorithm. So for CFD, we know those are going to be the gas dynamics equations. They are the general equations that govern a fluid flow. They have three momentum equations, a mass conservation equation, and an energy equation. And anything beyond depends on your physical process. If you have reactions, you have to add equations for your reactions. If you have fluid structure interaction, you have to figure out how you pass the forces from the fluid to the solid and how to solve what's going on inside the solid. Okay? But also this step involves a solution algorithm, because your equations may be formulated correctly, but there may still be a step that's missing. So you could have, I'll show you in a second, you could have 4 equations and 4 unknowns, but one of the unknowns doesn't have an equation. So how do you find that unknown? So you have to tweak your equations a little bit so that these equations are readily available to be implemented on a computer. And the last step is, in light of the nature of these equations, so is convection dominant? Is your Reynolds number high or low? Is diffusion dominant in your problem? In light of those equations of your mathematical model, you want to pick the correct numerical method and correct properties of the numerical method to solve these equations. Okay? This all sounds all kind of, just kind of very fluffy and hand-wavy. We're going to get into the guts of all of this. And then, at the end of the semester, you come back to this lecture, you're going to be like, yes, this makes sense. But there are 3 big, well-known, common methods used in CFD: finite difference, finite volume, and finite element methods. They're the most widely used. Finite volume is the most popular, and we will end up doing finite volume methods in this class, but we'll start with finite differences. Unfortunately, we won't cover finite element methods. There's a course in mechanical engineering for finite elements, but there are other methods like spectral methods, boundary element methods, control volume, finite element based methods, all of these complex methods, but they're all kind of share similar features. Okay, in the end, what changes is the way you are approximating your unknowns on the discrete grid. Okay, so let me give you an example of this process. Okay, I want to look at the flow over what we call a square cylinder. So think of this as a bridge, and there's cross flow coming in. There's wind blowing in this direction. This flow is laminar as far as we're concerned, and it is incompressible. Okay, there's nothing complex going on. There's no reactions. There's no compressibility going on, and this in fact simulates the Tacoma Narrows Bridge. Has anyone heard of the Tacoma Narrows Bridge? Yes. So what happened with the Tacoma Narrows Bridge?
The way I understand it, it had something to do with the frequency of
Yeah.
Right.
Yeah.
Right.
So, okay. So you remember? Yes. Yes. So you remember the von Karman Street, the flow over the cylinder? So at a certain Reynolds number, a laminar Reynolds number, the flow is going to develop vortices behind an object, okay? And in fact, it's going to develop what's called an alternating pressure gradient. So the pressure is going to alternate positive and negative, positive and negative. And it's going to cause this vortex shedding that's going to cause some frequency frequent change in the direction of the flow behind the object. So let me show you the Tacoma Narrows Bridge. So this is true footage of what happened at the bridge. So this is the bridge. There is flow coming in this direction, and this is the bridge. It started vibrating. This is all caused by the fluid flow. I don't know why they have this music on it, but yeah, there was a car left on the bridge. I mean, this is pretty scary. Can you imagine the Golden Gate Bridge shaking like this if there was a storm? Or like some crosswinds? And it keeps doing this for a while. It's a long video. Look at that. Oops, sorry. Okay. I'm going to try to go to the point where it just collapses. Anyway, history, this bridge collapsed because of complex fluid flow. But the flow is really simple to model, okay? So now we identified that this flow is incompressible and laminar. The next step is to develop a mathematical model for the flow. And this is the mathematical model that, actually I did use this, I did this as my final year project when I was an undergrad student, but I did it in 2D. I took a cross section of the cylinder, square cylinder, it was a square, and flow over a square, and looked at the frequency of the vortices being shed behind the square cylinder. Anyway, incompressible laminar flow, negligible effects of gravity. These are the governing equations that govern the fluid flow. We are looking at three velocity components or momentum, u, v, and w. U is the velocity component in the x direction. So if a fluid particle is moving like this, it's going to have a component in x, and y, and z, v and w. These three terms we will learn. They're called the convective acceleration terms. They are how they describe how the fluid moves using its own velocity, okay? Then on the right-hand side, you have a pressure gradient, dp dx, dp dy, dp dz, and a Laplacian for the velocities. So this describes the stresses or the forces acting on fluid elements. And we will talk through those in the next lecture. And finally, the mass conservation equation, okay? This is great. In compact form, we write these in vector form. And you will need to brush up on your vector calculus and all of these good things. But anyway, in compact form, this is how we write the equations. Div u equals 0, that's mass conservation. And the Navier-Stokes equations for the vector velocity u, uvw. So these are three equations. Okay, so now this is the mathematical model. But is it ready to go to a computer? No, because we have four unknowns, u, v, w, and p. Remember, the density is constant because the flow is incompressible. There's a typo there. This should be there should be no rho f over there. So we have four unknowns, u, v, w, and p. Mu, the viscosity, is constant, and rho is constant. We have four equations, 1, 2, 3, 4. But we have no equation for the pressure. How do you calculate the pressure? So this is where you have to develop an algorithm to extract the pressure from these equations. And this happens at the mathematical modeling step or between that step and the numerical method step. There's a guy from Seoul University who did a numerical simulation of the Tacoma Narrows Bridge recently and published it in the Physics of Fluids. Sorry, from Seoul National University. And so, you know, he describes what's going on. So it turns out that there was fluid structure interaction over the bridge, and he ended up simulating the flow. Look at that. So he took the bridge and got the properties, put it in a fluid, in a computational code, and solved the Navier-Stokes equations for the flow over the bridge. Now, as these vortices are developing, they are creating a fixed frequency. Now, see the colors on the bridge. Those are describing that wave, longitudinal wave, up and down. And then, after a certain point, as the forcing frequency starts resonating, you start creating the lateral vibrations. So this is just to show you that, you know, this is doable. Now you start seeing the vibrations, the transverse vibrations. Okay. Now, of course, to do this, you need a very complex code. But in principle, it's easy. You're just solving flow over an object, and then you take the forces of the flow on that object, put them in a solid mechanics solver, and solve for the stresses inside the solid, and that's it. There are other aspects of CFD, and that's verification and validation. We'll talk about these in the advanced topics. But to do CFD, you need strong knowledge of fluid dynamics. Okay, I'm not here to teach you fluids. I will touch on some fluid dynamics issues, but it is up to you to get there. And we're talking graduate fluid mechanics, not undergraduate. Okay? Now, I put a few resources on my website. tonysad.net. I'll show the website on the next slide. But there are two great sets of films that give you an intuitive understanding of fluid mechanics. One by the National Science Foundation and one by the Iowa Institute of Hydraulic Research. Very well-known fluid dynamics movies. Go and watch them. Put them, put your earphones and, watch them while you're driving. No, don't watch them while you're driving. Watch them while you're, hanging out, while you're resting. Pick up any gaps in your understanding of fluids. Okay, we're going to do a lot of math with fluids though. Strong knowledge of vector and differential calculus. If you feel you have any gaps, you have to pick those up. Understanding of divergence, curls, tensor, what tensors mean, all of these concepts. You have to master those because we cannot spend a lot of time on trying to understand what these mean. Strong knowledge of partial differential equations. So although this course doesn't get into the theory of partial differential equations, you have to understand what basically that PDEs are time and space dependent equations of things in life. Strong knowledge of linear algebra and programming. So we will use exclusively Python in this class, and specifically Jupyter notebooks. We'll have a chance to discuss this next time. But the plan for this class is, first we'll start with motivation, then next few lectures we're going to go over the governing equations. We'll try to do those in 1 or 2 lectures or 1.5 lectures, just to summarize what we're trying to solve. But mastery of the governing equations is essential. You need to understand when you say, oh, this is an advection term, this is a diffusion term, this is a source term, this is a gradient term. Diffusion is stronger than advection in this case. You need to understand these concepts. So, and as we go through, I'll share with you my knowledge about these, but you have to essentially kind of have a solid understanding of the governing equations. Then we will start doing basic pneumatics. We will take the Navier-Stokes equations and rip them apart, okay? And we'll identify advection, diffusion, nonlinear advection, and then advection, diffusion. We'll combine those together and try some basic numerical methods. And as we're doing this, you will learn or relearn basic numerical methods, okay? Then part 2, we're gonna hit, so I promise you probably within a month or 2, you're gonna have a CFD code on your hands that solves simple basic flows. But then we're gonna show that CFD code is not that accurate and has problems in it. And then we're gonna go back and rip through everything we did, okay? We're gonna go back to hyperbolic equations, that's advection, and we're gonna look at what schemes work for advection. If we have time, we'll look at flux limiters, and then try to solve hyperbolic equations and the Euler equations. Those are the compressible gas dynamics equations. Look at if we can capture shock, okay? So historically, this class never taught compressible flow, so I'm going to try to do that this year. Hopefully it works. And then finally, depending on how much time we have, we're going to touch on advanced topics. So CFD is not just about numerical methods. A big part is about numerical methods, but another big part is about modeling. Turbulence modeling wouldn't exist if there were no supercomputers to solve the equations of turbulence. Low Mach flows or slightly compressible flows where there's reactions and variable density, we're going to touch on those in the advanced topics. Verification, validation, also parts of it. So as of now, there's no, we may have 10 homeworks or we may have 2 homeworks. Okay? It's an open-ended course, and I want you to deal with that. You're taking a grad class, although some of you are undergrads, but I'm going to treat you as a graduate student. So, and as a graduate student, I can't tell you exactly what to do, and you have to deal with things being open-ended. So essentially, when something is open-ended, you have to figure it out on your own. So homework, we may have a lot of homework. We may have a few homeworks, depending on how you respond to me and how this class is going on. There will be a couple of projects, and there's no final. The final is going to be a project that you're going to take and probably adapt to your research and maybe do something that will be useful to you, okay? And we'll talk about this as we close through the semester. You can always please refer to my website, tsad.net. There's a link at the top, CFD. Click on it. You'll see the most recent updates, lectures, handouts. Again, I'm going to give you scans of the chapter, textbook chapters, and other material that you're going to need. There's plenty of resources there as well. These lectures, the slides and the audio will be posted on my website, but I will also use Canvas to put grades and probably communicate with you. So make sure you sign up for the Canvas and make sure your utah.edu email is working. That is the email I'm going to use to communicate with you. The books we will be using are these 3 books and maybe 10 more, but I'll send you handouts as needed. As I said, this is a graduate course, so I expect you to produce graduate level high quality results. When I ask for a report about a simulation you did or a summary of an article you read, don't just give me a paragraph, an unformatted paragraph in Notepad. I expect you to give me a high quality report. You are an engineer. You are essentially working in this class towards your grade, right? So I expect you to deliver high quality results, okay? Maybe the first time I'll let you know, hey, this is not acceptable, but second time it's a, I'm not gonna waste time on trying to, these things you should master, okay? I expect you to be professional in all your communications with me and your colleagues, and you expect the same from me. We'll address each other appropriately, we respect each other, and this is an open-ended course, like I said, so expect some research level, possibly in certain topics we're going to discuss, some open-ended questions that, there's no one answer. Different camps use different methods, and so you have to deal with that. And let's have a great semester. Thank you for coming in. It was a pleasure seeing you. I hope you don't drop the class. And we'll see you on Thursday. Thank you.